Hi everybody, welcome back. Today we're going to go ahead and we're going to finish off one of the sections that we were working on before, which was vector fields and line integrals. So on the screen here you see that the heading just says that it's continued from last time. And I want to take this table directly from the book, that's the Thomas Calculus. And this table actually goes through and it describes all these work integrals that we've been looking at very explicitly, right? The first one gives you, this is how we define it using the definition. Then if we want to use a vector differential form, we use this. If we want to use a parametric equation, then we go ahead and use this. If we want to use parametric scalars, then we use this. And if we want to just use a scalar differential form, then we use this form. Now notice all these 5 forms are equivalent to one another. So that's why I wanted to put this on here. That way you can all see directly that all of these forms, when we work with this type of line integral, are exactly the same. Alright, so there was this reasoning behind why we were going through mixed integrals that had m dx and dy, right? It's because at this point in time we start getting to see all of these vector fields kind of tie into these line integrals that we are essentially working towards. Alright, now down below you see this definition here that says let C be a smooth curve that's going to be parametrized by some vector positioning function, where T is going to be bounded on some interval between A and B, and let F be a vector force field, or let F be a vector field, excuse me. Alright, my apologies all, now I'm back. So once we have this smooth curve parametrized by some R of T over some interval for A and for T bounded by A and B, we're going to let F be this vector field, and it's going to be a continuous vector field over some random region that's going to contain the curve C. Then the work done in moving an object along that curve from point A to point B is given by this integral. Now notice this is the exact same line integral that we were working with at the end of the last video. So today what we're going to do is we're going to get an example going, that way we can start analyzing how, again, we are working with these line integrals and how they relate to work, which is moving a certain object or moving the curve through this vector field. Alright, so here we go. So we have this vector field here, right? And the first thing that I'm going to want to do is I'm going to want to parameterize, or sorry, I'm going to want to make a function composition of my vector field with my position function. And your position function is going to give you your x coordinate, your y coordinate, and your z coordinate. So all we then have to do is we then have to substitute it in to our vector. So this is going to be 2 times y. That y is sine of t. 3 times x. So that's going to be 3 times cosine of t. And then x plus y, that's going to be for our z coordinate here. So I'm going to have here x plus y, so that's going to be cosine of t plus sine of t, as such. Alright, so now I'm done with this function composition, at least for this vector field. Now what I want to do along with this is I want to go ahead and I want to find my derivative for my position function. Alright, so I'm going to go through and I'm going to find the derivative for this position function. Now my derivative here should be negative sine of t, cosine of t, and then this is just going to be 1/6, as such. So now what I need to do is I need to go through this part here and I need to go ahead and take the dot product. So I'm going to go through and I'm going to take the dot product between these two vectors. There we go, just like this. Alright, so this is going to be 2 sine t, 3 cosine t, and then we have cosine t plus sine t, and this is going to be dot negative sine t, cosine t, and 1/6, as such. Alright, let's go ahead and let's find this dot product. So multiply, that's going to be negative 2 sine squared t, and then we're going to have a plus here, so this is going to be plus 3 cosine squared t, and then we're going to have plus 1/6 multiplied by cosine t plus 1/6 times sine of t. There we are. All right, so looking good so far. Now, excuse me. All right, my apologies once again. So here we go. Now that we have this, now we can go through and we can start evaluating what this integral is going to look like. All right, so when we want to find the work being done in this particular case is just going to be the integral for my bounds from 0 to 2 pi. And this is going to be for this function that we were investigating in here. That's -2 sine squared t plus 3 cosine squared t plus 1/6 cosine t plus 1/6 sine t. And this is going to be dt. Now, one of the things that you can do here, we can use the power reduction rules for sine and for cosine in order to be able to evaluate this. All right, so there are some tips and tricks that we can use here that will make this nicer moving forward, but essentially from here you can all just keep going with this. All right, nice. So what I'll do is I'll leave this open and I'll say, hey, what I want you guys to do is I want you guys to then fill in the answer on the discussion board. That way you guys, I can see that you guys are doing this integral. All right. So not only do we look at not only do we look at work being done by this curve through this vector field, but we also want to look at flow. All right. We can look at flow moving through a vector field. Right, and that's what we're going to do next. Is we're going to define what what flow is, and how we want to look at that using line integrals. All right, so I'll give you a definition for it in just a bit. All right, so here we are. Again, we were looking at the flow of an integral before we were interrupted. Again, my apologies there. And during that time, I kind of had some reflection time to actually look at it, and I actually want to omit doing an example for this flow integral, because a lot of these examples for flow integrals are very, very, very similar to these examples, which is the work done by a curve as it's moving through a vector field. All right, they're very, very identical in the same setup, in the same process, and in the same type of integration work. All right, so I'm kind of omitting this piece right here. Even though you're going to have them for homework, again, the same setup is going to occur as we did before. Now, the one last item that I want to talk about in this particular section is that we're going to be looking at a smooth, simple, closed curve, and this is going to be in some domain for a continuous vector field. And this vector field is just going to be defined in R space 2 for now, which is just going to be some m and some n component functions for this vector field. Now, n, we're going to define lowercase n as we always have. This is going to be the unit normal vector that we're looking at any point in time on the curve C. And then we're going to define the flux. The flux of the force field, the flux of the vector field across this given curve is going to be denoted by this type of integral here. Either we can use this piece of information here if we have some vector field, and if we have a normal vector, then we can go ahead and we can use this process, or we can use this new notation here where we have an integral, and this integral that we look at is denoted with a little circular symbol right in the middle. Typically it has, Typically this has a directional arrow on the actual circle. That way it lets us know that, hey, it's going to be traversing through a specific curve. And m and n here are basically your vector scalar functions for this vector field. All right, so the example that I want to look at here when we're talking about finding the flux. this whole idea or this whole concept of finding a flux stems from the ideas or the properties that we have when we're trying to establish how much of a certain item is flowing through a portion of a surface or a curve or a volume, anything like that. So find the flux F if we have this function x minus y in the I direction plus x in the j direction across the circle. X squared plus y squared is equal to 1 in the xy plane. Alright, so we're going to go through here and we're going to start identifying what we have so far. Alright, now if I want to find the flux, alright, so I'm trying to find the flux that is occurring here. So this is going to be the integral of this vector field with the normal vector over the curve, and that's going to be with respect to its arc length. But I can view this as just this flux integral over the curve for m dy minus n dx. Excuse me. Now again, this m dy and n dx, this is going to come from this specific observation. This piece here in the I component, this is going to be your m component, and in the j component we're going to have our n component. Now what we're going to do is we're just going to make our substitutions here to figure out what we need. Alright, so we're going to go through and we're going to start making these substitutions. Alright, so I'm going to have some integral. Typically if we're looking across this circle, then across the circle we can choose some parametrizations. The parametrizations that I'm going to be choosing here is going to be that x is equal to, in this case it's going to be cosine of t, and y is going to be equal to sine of t. This will make sure I get my circle here, and I'm going to parameterize this because it's a whole circle. I'm going to go from 0 to 2 pi. And if it was any portion of the circle, then I can go ahead and I can figure out what angles that's going to be bounded by. So when I'm looking at r of t, in other words, this vector position function for my circle, this is just cosine t sine t. Now if I look at its derivative, and I'm going to want its derivative in a little bit, it's negative sine t and cosine t, just like that. And the reason I say I want the derivative now is because what I'm going to do is I'm going to do my parametrization here. So this curve is going to go from 0 to 2 pi. My function m was x minus y. But according to our work, x is actually cosine of t, so that's cosine of t. And then minus y was at sine of t, so it's going to be sine of t. There we are. So in this particular case, this was m. Alright, now we need my dy. So when we're looking at dy, then we're going to look at the differential for the y component. The differential for the y component is that cosine of t dt, there we are, minus the n component. N component is going to be this value here that we're looking at. So that, or sorry, this value here is the n component, which is just x. So the n component is just cosine of t. There we are. So that was my n component, and then I need my dx differential here. That means this is going to be negative sine t dt. And again, I'm going to outline what was taking place here. So this in here was this x minus y. Alright, and this in here was this x, simply because this portion here was our m, and this portion here was our n, like such. This part here was our dy, and this part here was our dx. So if we simplify this, or if we clean this up just a little bit more from 0 to 2 pi, there we are, I'm going to go ahead and I'm going to distribute everything that I can. So I'm going to get cosine squared t minus sine t cosine t. I'm going to factor out this dt all the way to the end. And then I'm going to have here minus and minus. That's going to be a plus. That's going to be cosine t sine t. And this is all going to be dt. Just like this. Which is really nice because this is just, again, 0 to 2 pi. And it's going to be cosine squared t dt. Now again, we want to use a power reduction. So when we use a power reduction to solve a cosine squared, we just look at 1/2 plus cosine of 2t, and then we're able to go ahead and integrate this specific piece. But as you keep going, you're going to find out that the answer is just pi. Awesome. So this is the whole idea for flux as we're going to be moving through a specific curve. At a later point in time in chapter 16, we're going to want to revisit this whole idea of a flux, but instead we're going to want to look at a flux when we're talking about a surface moving through a vector field. All right, so I hope you all enjoyed this continuation for this section, and we'll go ahead and stop here for right now, and then I'll go ahead and I'll start looking at the next section. That way we can go ahead and work with that section as well. All right, so hope you guys enjoyed it.